Okay, so we're going to come up with a general process whenever we have a differential equation in this format. So we're going to get a little heavy on the notation, a little heavy on the derivation piece, but relax. There's going to be an example coming up, so if the variableness is a little tricky to follow, that's okay. It'll hopefully make more sense when we start putting actual examples in there. Okay, so we want to solve this general second differential, second order differential. So we define, just like the last example, that y is u of x times y1 of x. And then it follows that y prime is uy1 prime plus y1 u prime. And similarly, if we find the second derivative, that is u y1 double plus 2y1 single u prime plus y1 u double. And if I go back and evaluate the original general format, so y double plus p of y single plus q of y. So that's u y double, so y1 plus 2y1 single y prime plus y1 plus p. That's u1 plus y1 u prime plus q of y, and y we said was u of y1. Okay, so if we do a little combine like terms, we should end up with something like this, where it's the u terms. We can group those and factor out the u, so we should have y1 double plus p y1 single plus q y1 plus y u double, and then all the y primes, we'll group those together, so that would be 2y1 prime plus p y1 u prime equals 0. Alright, now we initially, can I highlight this, we had the original statement that that whole expression equals 0, so that whole expression has to also equal 0 based on what we've seen. So that's going to give us y1 u double plus 2y1 prime plus py1 u prime has to equal 0. Alright, and then we're going to do a little trick we did last time, because maybe we don't recognize quite what the pattern is at that point, but if I do a quick variable swap when I set w is equal to y prime, then that means w prime is equal to y u double prime. And then I'm going to copy this over so I get a little bit more space. Okay, so copied that over, and then I did the variable swap, and now the question is, what are we staring at? And this looks like something we can do as either a linear differential equation or a separable differential equation. So it kind of depends on which approach we want to necessarily go with. I think separating. Yeah, I'm going to do that. Let's do separating. Okay, so separating means I'm going to put that on the left. And we'll put that on the right. And then if we separate, let's see, that means I'm going to get y prime over w equals negative 2 y1 over y1 plus py1 over y1. Sorry, just went back to my notation. There's a y prime. All right, so I'm going to move my derivative terms over. So I'm going to do a quick rewrite. So I can rewrite this as dw over w plus 2 y prime 1 over y1 dx equals negative p. That whole thing was distributed there, negative p dx. And then I will integrate both sides. Okay, so I do feel like I want to clarify. I'm taking the integral of everything on that side, and so dw over w, that's ln, so ln of w, and then that's ln of y1. And then on this side over here, I can bring out that, but p itself is potentially a function of x, so I can't quite treat that like a constant. So I'm just going to leave it as the integral of p dx, knowing that we're going to pick up a constant at some point. But that's okay. We're going to play with our ln properties here in a second. All right, so if I do a little combining, that's ln of w y1 squared equals this lovely thing. And since I'm trying to solve for w, I want to use my e rule here, so I'm going to raise that all to the power of e. So that's going to leave me with wy1 squared equals e to the negative integral of p of x dx plus c. Now we have seen that process before where it's plus c to raise to some exponent of e. So we're going to convert that into a different constant. We're just going to call that c1 out front. So let me copy this up here. So w y1 squared equals c1 e to the integral of p dx. And if I solve for w, that'll give me c1 e to the integral of p of x dx all over y1 squared. And remember, w is equal to u prime. So that means u prime is equal to this lovely fraction here, p of x dx. Why not? Which means u is equal to the integral, and we'll bring that c1 out, of e to the negative integral p of x dx all over y1 squared, that's dx. And then that'll pick us up another constant plus c2. Okay, so in general then, y2 is equal to y1 of x times the integral of e to the negative integral p of x dx over y1 squared x dx. Okay, so now we've got a general way to find y2.